Alright, yes, that's true. Last time we talked about logarithmic decrement, so let's go quickly through the notes that we wrote last time. I'm going to share the screen. It's going to share. Alright, so we talked about the logarithmic decrement. We said that before this we were making the connection between the properties of the system and the response of the system, because from the equation of motion we were able to determine the equation of motion, and then from that we were able to determine the solution and then the response. But sometimes we have to do the opposite, which means we have to look at the response of a certain system, see how it vibrates in time, and from that response we should be able to determine the properties. And we can do this, for example, by using the logarithmic decrement. We looked at the formal definition of the logarithmic decrement, and we said that it is the natural logarithm of the ratio between two quantities, the amplitude at a certain time and the amplitude at one period after that time. So mathematically this is what we write: x of lowercase t divided by x of lowercase t plus uppercase t. Okay, so we started from this definition, and then from this we can determine the properties. How do we do that? We look at the solution. This is the solution that is valid when we have an underdamped system. Remember, zeta damping ratio must be between 0 and 1. So this is the solution. When we have this solution, we can simply plug here x of t on the numerator and x of lowercase plus uppercase t. Then we know the definition of the period, 2 pi over omega d. Any question? Excuse me. Hello? Okay. Okay, I was saying that we have to plug again the solution here and here, solution at an instant t and the solution at t plus uppercase t. And then we also know that the period and the damped frequency are related to each other through this equation. So we can use this equation because basically we can simplify the denominator. Once we make this simplification, we can plug back. Once we see this form, we can further simplify because these two are the same, and then also a is the same on top and bottom. Then we can simplify. We can also split this exponential function in the product between two functions, so which means that we can further simplify. We have natural logarithm of 1 over e to the power of negative zeta omega n t, which means it's the same of this one. Logarithm and exponential functions are one the inverse of the other one, so we can obtain that delta, the logarithmic decrement, is equal to zeta omega n t. We looked at the definition of the relation between period and damped frequency. We also know the relation between damped frequency and undamped natural frequency through the damping ratio. So what we can do here is to rewrite the expression of the logarithmic decrement as a function of the damping ratio. We know that the damping ratio depends on the on the damping of the dashpot, what we modeled as a dashpot. So basically here we can have the relation between these two quantities. Of course, as we said before, we use this method to find the properties starting from the response, which means we take this equation here and then we rearrange so that we can find the property of the system, which is zeta, as a function of the response, which is in this case the quantity delta, so the logarithmic decrement. So again, of course, this is valid when we have a underdamped system, which means that basically we look at the response. Qualitatively it looks like this. So we have the response at time t1, the amplitude at time t1, the amplitude at time t2, so we can find this delta, and then from delta we can plug here and we can find zeta. Make sense? Any question about this? We went through a simple problem, which is like the application, what we just said. So for that problem we knew the mass, we knew the elastic constant, and then we knew the amplitude at two consecutive times, like one after one period, the second after one period from the first one, and what we have to find is a damping coefficient. We know the relation between damping coefficient and damping ratio, so we can rearrange this one. From the responses we can find the logarithmic decrement, then we can plug here, and then we can find zeta. Here I just plugged all the quantities, so we have only one final equation, and then when we plug all the numbers, this is what we obtain. Make sense? Any question about this? Alright, if there are no questions, we can move to the next topic. So today is 2/24/2025. Alright, what I would like to start to talk about today is another method to find the equation of motion for our systems. So this is a method that we can apply when the geometry, typically when the geometry of the system is a little bit more complex, or when we have more quantities, like more parameters that are involved in the system. And this is the energy method. So we will start by looking at a couple of examples that are similar to the examples, actually the same, of the examples that we have seen so far, and then we'll see how we can extend this, how we can apply this to more complex systems. So the first example that we can look at is the example of the mass and spring. So let's assume we have a mass that is attached to the ceiling through a certain spring. Of course we have the mass m and the spring k. So here again we're going to apply the energy method, and we are going to use the principle of conservation of energy, which means that we have to be under the assumption that all the forces involved are conservative. So it means that no energy is dissipated through heat, pretty much. So it means we don't have friction with air, we don't have friction with any surface and anything like that. So again, conservation of energy. So if this is the case, so if we have conservation of energy, so we don't have like energy loss through, again, friction pretty much, what type of energy do we see in a system like this from a mechanical point of view? What kind of energy do we see? We see definitely potential energy, and what else? Exactly. So the two forms of energy that we see in a system like this are potential energy and kinetic energy. So the potential energy is typically indicated with letter V, and then the kinetic energy is typically indicated with letter T. This is, convention. So again, potential and kinetic. Now, going back to what we were saying before, so since we don't have loss of energy, it means that we are applying the principle of conservation of energy, so all the energy stays like within the system. We can bring this, we translate in a mathematical form, and when we translate this in mathematical form, basically what we say is that the total energy remains the same, which means that the summation of potential and kinetic energy is constant. So we will see that these two forms of energy, the summation of these two forms of energy is always the same. However, the individual, potential energy and kinetic energy, they can change during the motion of the mass in this case. But again, the summation of these two, it's constant. It is always the same. So basically, it means that if one goes up, the other one goes down, and vice versa. Now, what we have to do now, we have to find an expression for the potential energy of the system and an expression for the kinetic energy of the system. So let's start from the kinetic energy. How do we write the kinetic energy of a body that is translating? Yes. This is the kinetic energy. So we can relate the kinetic energy of the system to the velocity of the system. So it means that we have 1 over 2 multiplied by the mass and multiplied by the velocity squared. We know that our variable of interest is the displacement of the mass. So of course we can write the velocity in terms of displacement, which means that we look at the derivative of the displacement. So we have x dot squared. Makes sense? Now we have to find an expression for the potential energy. Now, what kind of potential energy do we have in a system like this? Yes, we have potential. Exactly. We have potential gravitational, so we can call this V grav. Anything else? Exactly. So we have two forms of potential energy. One that comes from the force of gravity, and the other one that comes from the spring. So we can differentiate these two because we have to include all the forms of potential energy. So from the gravitational energy, this again it depends on the mass of the body, and it depends on the mostly on the mass of the body, and of course this is how we are going to write. So we have negative mgx. Again, is related to the location of the body. And then for the spring, this depends on the elastic constant of the spring. So we have 1 over 2 k, and then the displacement of the spring is expressed as delta plus x squared, where delta, and we will see a little bit more in a minute about this, is basically the static displacement of the spring. We know that when we have a mass that is hanging on the ceiling through the spring, of course there is a static deflection. In this case it will be an extension, and this delta is exactly that static deflection. Yes. when the system is at rest, it means when the mass is not moving. Because remember, we are doing a dynamic analysis, which means that we are looking at what's going on when the mass goes up and down. But there is one equilibrium situation where the force of the spring perfectly balances the force of gravity. And we will see how we use this concept as well. So now that we have the expression of the kinetic energy, the expression of the potential energy, we can take these two and we can plug in our conservation of energy. So basically what we have is 1 over 2 m x dot squared plus 1 over 2 k delta plus x squared minus mgx equal to constant. Okay, what we can do now from here, we can simply derive this expression with respect to time, and let's see what happens. So when we derive this expression with respect to time, we have the summation of basically 3 functions. So we have to do the summation of the 3 derivatives, pretty much. So we start with this first term. So the derivative would be 1 over 2 m 2 x dot x double dot plus the derivative of this function here. So we have 1 over 2 k times 2 delta plus x times x dot, and then we have the derivative of these quantities minus mg are constant, so the derivative will be simply x dot equal to 0. The derivative of a constant is 0, right? So now we can simplify this expression, because we can get rid of these 2 here with these 2 here with these 2 here. We can also get rid of the x dot, because it appears in all 3 terms, and then we have equal to 0. So when we do this simplification, we have m x double dot plus k that multiplies delta plus x minus mg equal to 0. If we do this product here, we have m x double dot plus k delta plus kx minus mg equal to 0. What can we say now? So now we can say that we can go back to what we were saying before. Actually, we just talked a little bit about the static equilibrium. We said that in that condition, the force of gravity must balance so the force of gravity is pushing the mass down. The force of the spring is pulling the mass up. At some point, these 2 forces must be in equilibrium, which means that if we look at this expression, we will have the k delta is equal to mg, which means these 2 terms can be removed, so we can further simplify our equation. So what we obtain is m x double dot plus kx equal to 0. Here I'm going to put between parentheses that k delta is equal to mg for the static equilibrium. So if we introduce this, our equation can be simplified and becomes like this: mx double dot plus kx equal to 0. Is this familiar? Yes, it is, because this is identical to the equation that we found at the very beginning when we were looking at single degree of freedom and damped system. Remember, in that case we were using the equilibrium of all the forces involved, and we ended up with this equation here. Now we are using a different procedure, a different technique, but of course, since the system is the same, we must find the exact same equation of motion, which means that we will have the exact same general solution, and with the same initial conditions, of course, we will have the exact same particular solution. Make sense? Again, in this case, we went through, we analyzed a system that is pretty simple actually, but this method is very powerful for analyzing systems that are a little bit more complex, and we will see a couple of examples for sure today and maybe next time as well. Any question about this? Alright, if there are no questions about this, we can give a look at the second example. So in the second case, we will look at this one. Alright, what are we looking at? We are looking at a pendulum, right? So here we have a certain mass, m, and then we have that this mass is attached to the ceiling through a certain rod. And what we can do here, we can find the equation of motion by using the energy method. Can we do that? Can we try? So now this time I want to give you a few minutes before we can look at this together, so you can do a little bit of reasoning of what we should do, knowing this expression here, so summation of potential and kinetic energy constant, and looking at this system here. So please think about this for a few minutes. Alright, any idea on how we should approach this problem? Do we need to do that? Do we need to convert to you just said a tangential velocity. Do we need to do that? What kind of motion are we analyzing in this case? It's a circular motion, which means that what we can do in this case is the same that we did when we were using the force method. I don't know if you remember when we were analyzing the very first system, which was like a translational system. We used the mass to determine like the motion, and then when we moved to the pendulum for the first time with the forces, instead of looking at the mass, we looked at the moment of inertia, because this is basically the comparison between again translational motion versus rotational motion. And here we can do the same thing actually. So in the previous example we used the translational kinetic energy, which we defined as here 1 over 2 m x dot square. But in this case, since we are looking at rotational motion, we can use the rotational kinetic energy. Make sense? So, exactly like we started before, we start from the principle of conservation of energy, so we have T plus V equal to constant, and even in this case we have to find the kinetic energy T and potential energy V. How do we find the kinetic energy? As we just said, we use the rotational kinetic energy because the ball is basically rotating around the center of the ceiling in this case. So from a physical point of view, the expression of the kinetic energy is the same because we are of the translating mass, because we have 1 over 2, and then I, we can call this I0 for example, if this is like the origin of our coordinate system, multiplied by omega square. Yeah, for the translational motion we have 1 over 2 mv squared. In this case we have 1 over 2 I, which is the moment of inertia instead of the mass, multiplied by the rotational or angular velocity instead of the linear velocity. But physically, this expression is the same of the expression that we saw for the translational motion. Now, even in this case, of course, our parameter is the angle theta, so we can express this angular velocity as a function of the parameter theta. So this becomes 1 over 2 I0 and then theta dot squared. In that case we had x dot squared, here we have theta dot squared. We can also recall the expression of the moment of inertia of this object with respect to a certain point. So we have that I0 is the same that we used when we derived the equation of motion with the forces. So we have ml squared. So we have that I0 is ml squared. The kinetic energy T becomes 1 over 2 ml squared times theta dot squared. Makes sense? Now that we have the expression of the kinetic energy, do we have any potential energy in this system here? Yes, we still have the, yes, exactly. We still have the gravitational force that is pulling the pendulum back and forth, basically. So we have to find the potential energy related to the force of gravity. So we can have, in this case, we only have that potential energy. We don't have any spring here, so it means that we don't have like a elastic potential energy. So we can simply indicate the potential energy as V without specifying because it's only gravitational. So how do we write the expression of the potential energy? Assuming that we use this as a reference for our system, which is like the lowest point, how do we write the potential energy at a generic point here? Yeah, let's look at the height. You are getting closer and closer. We look at the height, and in general the potential gravitational energy is mgh, right? M is the mass, g is the gravitation, is the acceleration of gravity. What is h in this case? So h is the distance between the datum and the generic location where the mass is at that specific instant, which means in our case is basically this distance here, h, right? This is the distance. Of course we look at the distance in the vertical direction, So since we look at the distance basically between this point and this point, again in the vertical direction, so it means we are looking at this quantity here from, let's say, a geometric point of view. How can we find this distance here, h, looking at all the parameters of the system? Okay, let me help you. So we said that we have to look at the angle, we have to look at the length. So since we are looking at this distance here, we can find this distance as the difference between this distance here and this distance here. So the whole thing, when the ball is, at the very bottom, this distance here would be L. So we have, because it's the entire length of the rod, and then we have to subtract this quantity here, which is L times cosine of the angle theta. If we look at this triangle here, if this is the angle theta, again, this quantity here would be L cosine theta. Right? We can do the exact same thing that we did before. So we have the expression of the potential, kinetic energy. We have the expression of the potential energy. We can plug this in the principle of conservation of energy, and then what we obtain is the following: is 1 over 2 m L squared theta dot squared plus mg L minus L cosine theta equal to constant, because we are using this equation here. So what can we do now? The exact same thing that we did before, so we can derive this expression. Of course we derive with respect to the variable theta, so we have 1 over 2 m L squared 2 theta dot theta double dot plus mg. Of course mgl is if you do the product between this and this, mgl would be a constant, so we can get rid of it. So we have only the derivative of this quantity mgl cosine theta, so we have mgl sine of theta multiplied by theta dot equal to 0. Derivative of a constant is 0, right? Even in this case we can simplify our function, because we can divide both terms by m L squared and theta dot. So if we divide by m L squared theta dot and then we simplify 2 and 2 here, what we obtain is theta double dot plus g over L sine of theta equal to 0. Even in this case, we can do the same assumption that we did when we found this equation the first time. We can assume that we are in a condition of small rotation, small deflection, small angular deflection, which means that we can approximate sine of theta with theta. If we do that, what we obtain is theta double dot plus g over L theta equal to 0. Is this familiar? Yes, because it is exactly the same equation that we obtained when we were using the forces instead of the, in the first time to find the equation of motion. Which means that, of course, in this case, the natural frequency of the system is going to be the same, the response of the system is going to be the same. If we, the general response, if we use the same initial conditions, of course we will have the same particular solution and the same response. Makes sense? So if there are no questions, as I mentioned before, these are two basic examples that we can see when we look at the energy method. We can start to look at something a little bit more involved, and we can look at a problem, which is not this one, is this one here. Can you all see the screen? Okay. So here we have to use the energy method to calculate the equation of motion and the natural frequency of an airplane steering gear mechanism for the nose wheel of its landing gear. The mechanism is modeled as a single degree of freedom system illustrated in figure 51 or P1, whatever. The steering wheel entire assembly is modeled as being fixed at ground for this calculation. The steering rod gear system is modeled as a linear spring and mass system, K2, oscillating in the x direction. The shaft gear mechanism is modeled as the disk of inertia J and torsional stiffness K1. The gear J turns through the angle theta such that the disk does not slip, that's a very important point, on the mass. Obtain the equation in the linear motion x. Well, in this case we are using the principle is slightly different, because in that case you needed actually the second derivative of of the function that you find. So this is slightly different. Situations are different method. So we use the principle of conservation of energy, where we assume that again we are in a situation in which all the forces are conservative. So since all the forces are conservative, you only have kinetic and potential energy, and the summation of these two must be constant. So this is how you translate this mathematically. Again, T plus V equal constant, and then you can you can derive the function that you obtain, and then you obtain the equation of motion. I don't know if we will have chance to go through other methods to obtain the equations of motion, at least for discrete systems. Let's see, if we have time, we can also look at other methods. Sure. So again, let's start to look at this problem. I want you to think a little bit about this for the next few minutes, and then we'll do breakout rooms.